Thank you. Thank you everyone for coming, and thank you to Daniel for inviting me to speak. So I'm going to be talking about this result. The circle graphs are polynomially chi-bounded. So first of all, what is a circle graph? So a circle graph is the intersection graph of chords on a circle. And what that means is you start with a circle, and then chords are straight lines going across the circle, and you make a graph from it where there's a vertex for every chord, and two vertices are adjacent if their chords intersect. So the red chord intersects all other chords, and so as a graph, the red vertex is adjacent to all other vertices. And then just as a reminder, the chromatic number of a graph is the minimum number of colors needed to color it so that there's no edge between vertices of the same color. And the clique number is the size of the largest clique of the graph. And I'll be writing chi for the chromatic number and omega for the clique number. And so for this particular graph, this is now a coloring of the graph because there's no edges between the green vertices. And the size of the largest clique is 3 in this graph. And for every graph, the size of the largest clique is at most the chromatic number because you have to use different colors to color all of the vertices in the clique. And you say a class of graphs is chi-bounded if the chromatic number of graphs in the class is also at most of some function of their clique number. The class is chi-bounded if there exists a function f so that for every graph in the class, the chromatic number of the graph is at most f of the clique number. And so for chi-bounded graph classes, you get this nice relationship that the chromatic number is between omega and some function of omega. A really classical theorem due to Erdos is that the class of all graphs is not chi-bounded. So in fact, you have graphs of arbitrarily high girth and unbounded chromatic number. That is without any small cycles. So in particular, they don't have 3 vertices that are all adjacent to each other. And you can formulate a lot of classical results from graph theory in terms of looking at what graph classes are chi-bounded. So in particular, Ising's theorem, this says that the vertices of any line graph can be colored with at most omega plus 1 colors, is also saying that omega plus 1 is a chi-bounding function for line graphs. You don't have to be familiar with all of these theorems, but there's been a whole bunch of work in the area lately, particularly on induced subgraphs. But today we'll be focusing on the problem for circle graphs and for so more geometric type problems. So Garfish sort of popularized this notion of chi-boundedness in the 80s, and he was the first, and in part of that series of work, he showed that the class of circle graphs is chi-bounded. His function is about 2 omega, is about 2 to the power of 2 omega, so it's an exponential function that he showed. And we would like to see how good we can get the function to be. And for that, towards that end, we say that a class is polynomially chi-bounded if you can take the function to be a polynomial. That is, if the clique number is always, of any graphs in the class is always, if the chromatic number of any graph in the class is always at most a polynomial of the clique number. And then there's this sort of crazy conjecture due to Esperay, which has been this sort of asked to try and get people to disprove it. Like, no one, I don't know if even, I don't know how many people think this conjecture is true, but it's really important because we can't find any counterexample to it. So the conjecture is that every chi-bounded class that's closed under deleting vertices, that is, if you take a graph in the class, you delete vertices from it, it's still in the class. Every chi-bounded class like that is also polynomially chi-bounded. And so, in particular, circle graphs are closed under deleting vertices. Because if you want to delete the red vertex, for instance, you would just delete the red chord, and then the adjacencies don't change. And so this problem has been open since chi-boundedness became popular as to whether or not circle graphs are polynomially chi-bounded. And we originally wanted to disprove the conjecture of Esperay, but instead we proved that circle graphs are polynomially chi-bounded. And so we found a chi-bounding function of 7 omega squared. And in fact, the real function is omega squared times 1 plus little o of 1. But for this talk, I'm just going to be doing the 7 omega squared. So Darvish originally had this as the Chibounding function, and Kostoshka improved upon it. And this paper showed 2 to the omega Chibounding function for a slightly larger class of graphs, and then certainly improved on that bound a little bit. And this whole time, the best lower bound that's been known is of order omega log omega. So now we're starting to get sort of close. These are much, much closer. And we don't have, I go back and forth between which should be the right answer to this question. So the previous proofs all get 2 to the omega immediately by a technique that's known as leveling. So the rough idea of leveling is that you fix any vertex v in the graph, and then you partition the vertex set of the graph based on their distance to the vertex v. So the distance is the length of the shortest path, and essentially this is a breadth search tree starting at v. So you can use some techniques to show that for any integer I, if you look at the set of vertices of distance exactly I, the clique number goes down by 1. So for instance, in the neighborhood of v, certainly the clique number goes down by 1, and there are some techniques to show that that happens at any level. And then you use this coloring, yes, for circle graphs. It's a lot of different techniques, a lot of different proofs of Chiboundingness use leveling, but the second bullet point is specific to circle graphs. And actually, it's not quite true, but something very close to this happens, and it's enough to get the idea. And so then the coloring that you look at is you recurse, and you say, since the clique number has gone down by 1, you can color this part a little bit better, and then you double the number of colors you use by using totally different colors for even sets versus odd sets. So there's some set of colors used here and a totally different set of colors used in the blue ones, and so you double each time. The clique number goes down by 1. So you just immediately get the 2 to the omega, and all of the other proof techniques used use leveling. So before I go more into our proof ideas, it's easier for looking at drawings to look at a slightly different representation of circle graphs. And so that's going to be called an interval representation. The vertices of our graph are now going to correspond to intervals on the real line. So what you can imagine is taking your circle, putting a point somewhere on the circle, and then cutting the circle at that point and slowly deforming it until it looks like the real line. And then now there's an edge between 2 intervals if those intervals overlap. And what overlap means is that neither of the intervals is contained in the other. So these overlap, but these intervals don't. And neither do these. So in particular, just to get an idea of what cliques look like, cliques are a set of intervals that all pairwise overlap. And so that looks like something like this. Right, so this is just to get an idea of what cliques look like in these graphs. They look like that. All right. So if there's a point that's contained in every interval, then your graph is a permutation graph, and it's been known for a long time that permutation graphs have chromatic number equal to the clique number. So the proof of this takes about a page. It isn't too hard, but I don't want to go into it because it's been known for a while. But the point is that we are going to try to partition the vertex set of our graph into not too many permutation graphs because we know how to color them. So a permutation graph, you have, you number these points from 1 to n, and you number these points from 1 to n, and then the permutation you get from seeing how the chords go between the two. Yes, that's not the usual definition, but it is equivalent. So here's an example of something that isn't a permutation graph. Again, it depends on the representation. As in, an independent set, for instance, is a permutation graph because you could draw it so that all of the chords contain a single point. But the permutation graphs that we find, so for instance, this set of chords, this set of intervals is also a permutation graph, but that's all the permutation graphs that we find, though, will look like this. But this as a graph also isn't a permutation graph. There's no way of drawing this so that all of the intervals contain a single point. But what we can do is we can place a point somewhere, and we can color all of the intervals that cross it the same color of that point. And then the induced subgraph on these red intervals is a permutation graph. And now there's some chords remaining, but we can place another point. Let's make it a different color. And then all of the intervals that contain it are going to be colored blue. And now we've decomposed the vertex set of the graph into two permutation graphs. Now, it's too much to hope that you could use a bounded number of points, all of different colors, to get your permutation graphs. Because you can have graphs with clique number 2, but you can't place a bounded number of points that are all different colors to get all the chords. Right? You'd have to use a different color for this one, and for this one, and for this one, and so on. So we're going to allow 2 points to be the same color, but only if the intervals they color don't overlap. So I think about an example next. Okay, good. So what we're doing is we're placing points, we're coloring them, and we're keeping track of the order we place the points in. So the first point I'm placing in this picture is color red, and then I'm going to, from these points, I'm getting a vertex partition of the graph. So place this point, then color red, we color all of the intervals containing it. This point has to be a different color from 1, because otherwise these two chords would be the same color and they cross, and we don't want to allow that. But we could do this, and now this point can be blue again because there's no point colored by this point that overlaps with a point with an interval colored by this point. And then this one could be red. And now the rest of the uncolored intervals don't intersect any blue points, so I'm fine to place blue points and use them to color the rest of the intervals. So formally, the data structure we're keeping up is a set of points, a linear ordering of the points, and a coloring of the points, and it has this extra property that whenever we greedily color the intervals of the graph, as in the pictures, if two intervals overlap and are given the same color, then they're colored by the same points in P. And we say that this pillar assignment is complete if every interval of G is colored. So we're allowing pillar assignments to not color everything, just they're complete if they do color everything. So here's a forbidden configuration because these are overlapping intervals of the same color that are colored by different points. So this is exactly the configuration that we're not allowing. But something like this would be fine because the two overlapping intervals of the same color are both colored by 1. Okay? So let's go back to the picture of what these look like. The point of this definition is that because it's true for every 2 intervals that overlap, it's also true that for every monochromatic connected component, there's a single point contained in all of the intervals. And that means that every monochromatic connected component is a permutation graph. And so what we'll do to get our coloring, our final coloring of the graph is we'll use omega colors for each monochromatic component, and then we'll be using about 7 omega colors for the points. And that would get us our final 7 omega squared. So the real theorem is that every circle graph has a complete pillar assignment using 7 omega colors. All right. Now the real theorem is that So I'm going to say that one pillar assignment, A star, extends another one if A star is obtained from A by adding points later in the order. So again, in the pictures that we went through, we had already placed some points, and then a new pillar assignment extends that one if all of its new points are placed later in the order. And so the real trick here is that we have a nice inductive statement, which says that as long as omega is big enough, and here big enough is like 10 or something, I just don't want to worry about it for talk. Every pillar assignment with exactly 2 omega points extends to a complete pillar assignment using at most 2.5 times omega points. So this is an idea maybe you've seen some places. For instance, in Tomasson's 5 list coloring planar graphs, there's a stronger inductive statement about having a little bit less freedom on an outer face. And actually, I got this idea from reading a paper by Kim Kwan, Uman Sivarman, where you have a nice inductive statement to color one joints. So we started thinking about it for this problem. It's sort of, I mean, all of these proofs are sort of magical. Anytime you have a stronger inductive statement like this, they're a little surprising. Okay, so we're supposing the theorem is false, and we're considering a counterexample. And by a counterexample, I mean now both the pillar assignments and the graph, along with its representation as an interval overlap graph. And so we're considering a counterexample with the minimum number of uncolored intervals. So to go through the definition again, you have these points, they're ordered and colored. First you color the green ones, then 2, then 3, and then 4. And there's no 2 intervals of the same color that are overlapped and colored by the different points. So these are fine. They're colored by different points, but it's fine because they don't overlap. So now, because this is a minimum counterexample, all uncolored intervals are contained in one segment. So if there were uncolored intervals here and here, then you would consider deleting these uncolored intervals. And then because the counterexample is minimum, you could add more points in this part to get complete assignments. And likewise, if there were intervals also here, you would delete it and extend it to this side, and then you could join the two, because since we're adding things later in the order, over here doesn't affect this part at all. Okay? So all of the uncolored intervals are in one segment. Now, we're going to start by placing the points. Later, we're going to color them and order them. But now I'm going to place new points into this segment so that each part like this sees exactly 1.5 omega colors. And by sees, I mean that there's exactly 1.5. I guess I shouldn't have said this because omega has to be even, but it's not a big change in the proof. Just something really close. It's easier to understand it this way. So we want that the number of colors, so that there's an interval with an end in this part that's of that color, is exactly 1.5 omega. So here, there's one color, red. Here, just green. Here, just blue. And here, there's none. Alright, so we're placing these points so that there's 1.5 omega colors with an end in that part. And then first, let me show that we've added. You're right. That shouldn't be there. Yeah. Also, it shouldn't be 1. It should be like 4. I just didn't want to add too many things. That would be hard to see. So let's look at the first claim is that we have added less than 2 to the omega over 2 new parts. So first, I'm going to delete some of the intervals. I'm going to delete all uncolored intervals, and I'm going to delete all intervals with both ends in this part. So I'm just keeping intervals that go over 3. And note that I haven't changed this last fact because none of those intervals contributed to this count. So now this is a permutation graph because the point 3 is contained in all of the intervals. But let me delete a little bit more. For every new part, just keep one interval of each color. So there were 2 red ones that had the same part on the left. So I'm just deleting one of them. Again, deleting these doesn't change the number of parts that each new, doesn't change the number of colors that each new part saw. So there's still 1.5 omega times the number of new parts, intervals remaining. So here n is the number of new parts on the left. So now it's a permutation graph. And also, the main observation is that the maximum size of an independent set is at most 2 omega plus the number of new parts. So we have this special point 3 and some other points over here. And there are omega plus 1 there's about 2 omega points over here. There's 2 omega points, and so that means there's 2 omega segments between points also. And on this side, there are n dashed lines, n new points. And so if we look at an independent set, a little differently. So we deleted intervals with their endpoints in the same part on the left and the same part on the right. So that means that if you had something like this, its endpoint has to go beyond. And now, for instance, in this picture, there's no intervals with an end in this part because they'd have to go to the right. Sorry, there could be this one. The point is that what you get looks like a tree. Let me see if I can say that a little better. So you can show inductively that there's a part that only contains one interval. To see that, let me draw a picture again. So here was 3. And all of these, and these. So if there are at least 2 intervals in this part, it would have to look something like this. And now there could be this interval, but there's nothing else. There's no other interval that could exist in this part because it would have to go further beyond over here. But then you'd get a crossing, right? And we're looking at an independent set. Okay. So now, because these essentially look like trees, and trees can have a linear number of edges, and trees on n vertices have n-1 edges, we have that the maximum size of an independent set is just 2 times the number of parts on the right plus the number of parts on the left. And so putting this all together, there's this many intervals. The graph is perfect, and so you can partition it into this many independent sets, and each independent set has size at most this, and so that gets you this inequality. And then you cancel out the omegas and subtract n to get the n is at most 4 omega, and the only reason that we're using omega is large enough is because 4 omega has to be less than 2 to the omega over 2. So we're really not using very much there. So there are less than 2 to the omega over 2 new parts. So now here's where we're going to get in a log factor. We're going to take the middle point that's new and color it with a new color. Remember, we have a little bit of room. We've got 0.5 omega and new colors to deal with. And then do this again recursively. So on the left side, take the middle points and color it with a new color. And on the right side, take the middle points and color it with the same new color. So something like this. And just repeat this process until all new points are colored. And we will have used at most 0.5 omega new colors from the 2 to the omega over 2. Now, I just want to draw a picture again in a little bit more detail. So zoom in to this left side, the new part. We're taking the middle thing, coloring it with a new color, doing it again on the sides, and then doing it again, and so on. So we've used at most 0.5 omega new colors. And now maybe, so we can also choose to place these points so that something's been colored. And that means that, so we've colored more things now. So maybe there are still some things that are uncolored that are contained between 2 of these new points. But these between 2 new points, we've only used omega over 2 new colors. And we chose to place the new points so that they saw 1.5 omega old colors. And so together we have the 2 omega that we needed. So because we chose everything to be a minimum counter example, if you delete everything with no end in this part, we have a pillar assignment using 2 to the omega colors, and that means that it can extend to the inside. And so we separately extend the same pillar assignment to each of these. And so we get a coloring of the whole graph that way, and a contradiction. So that finishes the main proof. We were pretty excited about this because it's pretty short, but also I think it's really surprising to see how this inductive statement is exactly what you need. So this sort of idea for an inductive statement has been floating around, and there's also a nice theorem of Capoilius and Pock that essentially was this part, this line in the proof. They show something slightly weaker, but they do it in a more general case, and it's a really nice paper. So that's where we got the idea for this part. And then the inductive idea has also been around before. For instance, people knew that you can really quickly use this inductive idea to get a coloring using log the number of intervals colors. So all of the ideas have been around before, but somehow putting them together is exactly what you have to do. So there's I think it would be really nice to determine the Chibounding function asymptotically. Now that we're so close, it seems like maybe there's some hope. And I think it's also really frustrating that in some sense a log still shows up in the proof. We maybe have an idea for where a log could come from if only we can change a little bit. So I tend to think that the omega log omega is actually right, and the construction is also pretty difficult. The proof is almost as long as our proof of the upper bound. And then, so circle graphs are a nice case of what's called a vertex minor closed class. So graph is a vertex minor of G. It can be obtained from G by deleting vertices and by a sequence of local complementations. And the local complementation takes a vertex and replaces the induced subgraph on the neighborhood of the vertex by its complement. And so if you have a class of graphs that's closed under these operations, and it doesn't contain all graphs, and there's a conjecture due to Gielan that it should be chi-bounded. And Kim Kwan, Uman, Shivarman have proven this for if it doesn't contain a long path. And circle graphs are another basic class, which is an important vertex minor closed class. And so that's the other reason why we wanted to look at it, because we thought either we get a counterexample of this conjecture, or maybe this conjecture is true, that at least proper vertex minor closed classes are polynomially chi-bounded. And then finally, I'd like to try harder to get a counterexample to this by maybe looking at some other geometric problems. There's almost no progress on this for whenever you get rid of a graph as an induced subgraph. For instance, this isn't even known for graphs without a long path as an induced subgraph, which is sort of the first case. And now we have a little bit of an end towards looking at the problem for geometric graphs. So in particular, the next case to look at might be, so Bartosz Walczak mentioned this to me. So it would be the intersection graphs of L shapes. So you have the real line, and then an L shape is this shape, and it has to start at the x-axis. And then again, you put vertices for each of these shapes and an edge between them if they intersect. And it's still true that if you put a point somewhere and look at everything above it, then that gives you a permutation graph. So there's, which is generally false for other intersection classes, but for this one we have a chance, maybe. All right, thank you.